Our last collision, momentum problem, deals with a perfectly inelastic collision. This means the objects stick together after collision and move off together with a common velocity. They are the reverse of recoil problems. They tend to be, by themselves, one of the easier types, but since they're usually combined with other problems, they tend to be longer and a little more difficult. We're going to analyze a ballistics pendulum. Ballistics pendulums were designed to measure speeds of bullets when you couldn't have nice chronometers put at the end of your gun. How did they actually work? Well, let's draw a little picture which will be similar to what you have seen online. What we'll have is something that has a large mass, a large block of mass M, and we are going to fire into it a small bullet of mass little m, moving at the velocity we wish to know, v0. What will then happen? The bullet will lodge in the block, and the system will swing up through a height h. So we have a bullet in the block, m plus m, swinging up through a height h. And I'm going to tell you that the only three things we need to know or need to measure are the mass of the bullet, the mass of the block, and the height swing. Knowing those three things only, you can determine the initial velocity of the bullet. Now, why is this two problems? Take a look at especially h. H is a height. You can think about it as also just a distance. That can't be found in a momentum problem. Momentum problems deal only with masses and velocities. So we have to figure out where the momentum problem exists and where this other type of problem exists. If you remember, we can only analyze momentum immediately before to immediately after a collision. So in this case, here's the momentum problem. Let's call it 1, momentum. Immediately before to immediately after. So what happens immediately before? A bullet of mass m, moving at velocity v0, colliding with a large block of mass m, not moving in this case. Let's call this positive x. And right after collision, notice what's going on. No movement, no swinging. We have m plus m moving at some final velocity. That's the problem. We can't talk about height. So basically what's happening is the bullet lodging in the block gives the system a velocity after collision. Well, let's write our equation. Pi equals Pf. And in general, what would we have? If we call this one object 1 and object 2, we would have an equation that looks like this. M1 V1 initial plus M2 V2 initial equals M1 plus M2 V final. The opposite of a recoil. Now for this problem, since we called 2 the block, this term is 0. So substituting in, we have M V0 equals M plus M V final. Now, no matter what, the second part of the problem, we can't find V0. We cannot find the initial velocity of the bullet because the bullet is no longer by itself. So the only way we're going to get V0 is through this equation. The initial velocity of the bullet is little m plus big M times the velocity after impact divided by little m. We can measure m and m. Again, remember, this is big M. I should make it look big so you can tell. And this is little m. The only way we can calculate this is if we knew the velocity after the collision. So the collision is done. Once the collision is done, what do we have? Let's draw a picture. The collision is done. We have a bullet in a block moving up to a height h. We have a pendulum. So we need an approach to analyze a pendulum, which we've looked at in previous chapters, and this would be conservation of energy. Now, since we can't analyze any types of friction, the friction of the bullet going into the block has already been completed. Yes, is there friction in real life? Just as discussed previously, sure. Probably up in this joint up here. We can't analyze that. We have no idea what that is going to be. We've already discussed before how the rope does no work. So we can actually deal with this as only conservative forces. In fact, gravity is the only thing we care about. So how do we set up our energy problem? Well, here's the equation. KE initial plus PE initial equals KE final plus PE final. Initial, final, P due to gravity 0 here. Now let's make sure we know what we want. We want this initial velocity. The initial velocity in the energy problem is the final velocity in the momentum problem. All because they're labeled differently means nothing. They represent the same instant in time, the velocity of the bullet block combo after collision. So let's see what we know. From previous energy problems and analyzing these pendulums, for this case, what do we know? PE initial is 0, KE final is 0, because it has to stop. So what do we end up with? M plus M is the mass, 1/2, V0 squared equals M plus M, G, and the height change is H. We know that. Well, what happens? By to the masses. And we end up with V0 is root 2GH. This is the velocity after collision. So this is VF in the momentum problem. So going way back up here, here's what we have. The velocity of the bullet can be found this way. V0 equals the mass, M plus big M, the final velocity, root 2GH, that whole pile over little m. So it looks sloppy, but it isn't. Notice the only things you need to know are the masses and the height. There will be many variations on ballistics pendulums. Sometimes the back end of the problem. I consider the back end of the problem the non-momentum part. For in this case, it's an energy problem. Sometimes the back end is different, where you have to use a different approach. Sometimes the momentum problem is different. For example, if a bullet goes through a block. But they're all very related.